Hey everyone, thanks for hopping on today from wherever you might be calling into. I'm going to talk more about physical AI in practice, diving a little bit more deeper into some of the actual problems we're seeing in the field and how we're dealing with them, piggybacking off a lot of what Katie said, but now maybe on a little bit more of a hands-on deployed version of it. We're going to be using a lot of the same tooling as this is a talk in conjunction with NVIDIA as well, as we've been co-developing what we are calling the Physical AI Workbench together. But before we can get to all that, a quick before we get started here. If you weren't here in the beginning of the call, or maybe you have some short-term memory loss, who is Voxel51? Voxel51 is the lead maintainer of the open source tool FiftyOne. We have several millions of downloads on the open source tool, as well as it's very easy for you to get started. Just a quick pip install FiftyOne, and you can get started with your computer vision workflows locally on your computer. If you don't know what a voxel is to a video what a pixel is to an image. It's that volume element that gives it the time space elements. And if you don't know what is with the FiftyOne, if you're new to our meetup series or you haven't heard the story before, the origin of the story for FiftyOne comes from one of two tales, depending on who you believe, between our two co-founders. Co-founder one will tell you that, Brian Moore, that he thinks all the best future tech of the world is going to be done in cool top secret labs for AI. And what better top secret lab to name it after than Area 51? Now, if that's not really your cup of tea and you prefer a different, maybe more fun example of it, our other co-founder Jason says that he just had 50 bad ideas until he had 51. So choose your own adventure there. But my name's Dan. I'm an ML engineer and developer evangelist here at Voxel51. I've been working in the physical AI space for quite some time now, and I'm excited to bring you guys today some of the troubles and kind of solutions that we're finding in the field today across all different types of ADAS, drones, robots, and more. So jumping into that, what is physical AI? Type in the chat here if you've heard of physical AI before, if you're familiar with it, or maybe if you're just starting to get started with it. It is obviously something that's very new, and I kind of want to take a minute here to kind of explain why we have this new term and why it's not just another buzzword that we're kind of talking about this week. So we have to go all the way back to AlexNet to kind of ground ourselves about why, we're where we are today. After that AlexNet in 2012 model, computer vision from deep learning perspective really began to take off, right? We were now able to use machine learning models to accurately classify images from a number of different classes. But grounding ourselves back then, it was a very different problem than it was now. I don't want to use the word simple because it was still very complex back then. But back then, we were kind of just looking at JPEGs or PNGs and then saying cat or dog, right? Look at the JPEG, cat or dog. That as we grew and evolved over time, though, we started counting the dogs, we started segmenting the dogs. But one thing that was core to the problem as we move into the perception AI space is you're really looking at a single piece of media and making a prediction on that piece of media, right? You're looking at a JPEG, making a prediction. Even if you're looking at a video and then you make a prediction. This is going to change as we move on, but before we can get then, we have our ChatGPT moment, of course, as everyone's familiar with. Gen AI comes out. It's really great for writing blogs. It's really great for generating pictures and all this stuff. And it's really transforming the landscape of AI as we knew it. This is going back a couple of years here. And of course, the boom of all the agentic workflows and everything like that takes off after that, where now I can give AI a task and it's going to be able to perform some kind of action on this. So you pair this with Gen AI, I can now give it a set of instructions as a prompt, and now not just as a prompt and get an answer right away, but I can give it a prompt for agentic AI and have it take a set of actions, right? I can say, I need to buy a new jacket. I want a red jacket. The agentic AI is going to be able to go through, go shopping, look at a bunch of different websites online, find a bunch of jackets. It's even going to be able to pull some of our past conversations, say, oh, I know Dan is a size large, and he's going to make sure that he gets the right jacket for me, my agentic AI, until we can finally make that decision of buying a jacket. And this is kind of where we were up until 6 or 7 months ago, maybe a little bit further back at the start of the year, where we have these agents. They're able to look and understand and take actions. We call these vision language action models. Where we really are turning the corner here with physical AI is that now we're dropping this into a physical component. There's an actual physical real world interacting model, that these actions are not an action that is happening online. It's not, organize my files. It's not go shop here. It's not balance my Excel sheet. This action that it's taking is moving through the world. It's driving. It's dodging a pothole. It's picking up a box. It's flying a drone over a cornfield. And this is where we haven't seen it before. And why this is so revolutionary in difference, it is because of the level of complexity that has evolved since here. I go all the way back to the start of this conversation to say we were looking at just a JPEG and saying cat and dog. Now, when I am in a car and I see a pothole, yes, I'm still looking at a pothole and saying that's a pothole. There is the pothole. But now I am funneling in 50, 100, if not hundreds, thousands of different sensors from my car, such as velocity, acceleration. Am I hitting the gas? Am I hitting the brake? Where's my GPS? What does my LiDAR say? What does the left camera look like? What does the right camera look like? All these different sensors that are all working in unison to pass into a single model that are going to interpret the physical world around itself and then take an action accordingly. This is something that we just haven't seen working in a single model orchestration like this in the past, and it definitely is worth its own category now, where the complexity has rise so much. It's so much more than just a pure perception model. We're taking in all these physical sensors to best get the physical to digital representation for our model to make the best actions on. And that's really what physical AI is all about here. Why are we having this problem in the first place? Why did we not stick with the perception models of the past when they were good enough? Well, the question is really, why is 97% not enough? Or in other words, why don't we have self-driving today? If you don't know, self-driving has actually been around for a very long time. Even before, the transformer models and attention is all you need, Waymo was driving self-driving cars in San Francisco with just pure basic computer vision models. The reason why we didn't have self-driving cars then and why we still don't have self-driving cars now is that these models hover somewhere between 90 to 97% accurate across a whole global scheme or global standard. This is obviously not enough, as I'm sure many of you out there wouldn't feel comfortable hopping into a car that is only 97 or 98% accurate because the 2% is so much more important than other classical computer vision models that are being deployed in labs or in B2B programs or whatever it might be. That 2% represents real human lives and people that are at risk when these models are deployed. And the reason why we can't get all the way to 100% is for a whole number of reasons that we can't just quite capture in pure perception systems. An example is our angry, reckless driver here at the top. When do I teach a model to break the law, right? A car is driving at me on the wrong side. I need to swerve into the wrong side myself to dodge this car. And how is the best way to do that? Another example here is a tire rolling down the road at me. Well, I've taught my perception system, hey, we see tires all the time. In fact, there's 4 tires on every car for the most part. So don't do any corrective actions every time you see a tire. We see tires all the time. So what makes a good tire versus a bad tire that's loose and running down the road and going to hit me? Add on top of that things like jaywalkers, weather conditions, strange traffic patterns in different countries, and you'll start to understand why we can't just solely rely on perception systems and really good logic. We need to teach a model physics. We need to teach the model real world, right? This idea of world models, and use that world model to then drive the decisions that our car or physical AI or robot or drone or whatever it is going to be are going to take afterwards, right? And the idea is that if we teach the model what the world works, how the world works, similar to what Katie was presenting earlier, then the model will be able to take the right action throughout that world. However, as you can imagine, this is a very difficult problem. And one of the most important, if not the absolute most drastic reason about why we can't do this today is because of bad data. There is so much bad data out there that even as Katie said, when you scale to internet-sized data, you're still not going to be able to get to self-driving cars because within that internet scale amount of data, there's just so much garbage. Sensors miscalibrate. You have poor situations of visibility, or it's, you're training on you pulling out of the garage for the 100th time. We don't need to do that. We really need to get to these long tail out of distribution, 1 in a million scenarios to train our car on so that when that 1 in a million happens in real life, we're able to take that corrective action. These are things like removing model bias issues. We need to make sure that our car works in all scenarios, across all cultures and all locations, or else you're going to have actual lethal physical danger, right? That is the most crucial part to drive home, that this is more than a computer vision problem. It's more than an academic, cool problem to solve. This is one of the greatest humanitarian causes that we are trying to solve today, right? If we can remove car accidents as a cause of death, that is going to be removing the number one cause of death outside of disease in the entire US, if not the whole world. So this is a problem that is requiring not only a tons amount of resources, but a ton amount of care, safety, and thought that goes into it before we deploy these models into the real world. In fact, this data problem is dragging down almost all these data teams that we see today in production. 39% of their time is wrangling this data, whether it's zip files that my coworker has sent from me, or trying to dive into an old notebook to load in that data set and visualize it again, or trying to make structure of an unstructured data set. It's just simply impossible to try to dive into your S3 buckets and try to understand all these different images. And because of this, in fact, 50% of simulations in production fail due to poor data quality. Whether it was just a garbage scene, as we'll see in the future from the start, or there was a miscalibration, or as we found in some cases, your data pipeline was always broken. We had a case in one situation where we had a really shocking discovery from a very prominent automaker that I'm sure everyone here would know if I was to name them. I will not. That all of their data for the last 3 years has been not correctly calibrated going into production. And this is the problem that we're seeing, and we're going to talk about how we solve it in a second here, is that synthetic data jobs and really physical AI training jobs are failing consistently because of poor quality. You're not getting over that gap. And the data comes off the autonomous vehicle and it's instantly getting siloed to each team. You can imagine if you're on the self-parking team or if you are on the cruise control team, you're actually doing very similar tasks here, right? I can't hit the car in front of me and I got to make sure the car behind me doesn't hit me either. So if you guys are working on such a similar task, why do you guys never share data? Why, this is something I see over and over and over and over again, that these physical AI systems are taking in 100 different inputs, right? But if I'm working in self-parking, I might only need 75 of them, and cruise control only needs 54 of them, and someone else only needs a certain set themselves. So what happens is they completely Frankenstein the data pipeline specifically for their individual team's use case. And what this means is that you're not able to spread the innovations across your organization and across your team. I challenge a lot of my customers, hey, if you have this 10x engineer or you have this really great breakthrough, it's a data pre-processing step, it's a new model training program, it's something like that. How long does it take for you to get that innovation to all the other teams? And usually the answer that I hear, I say, is it weeks? Is it months? Is it never? And typically the answer is never. They can't share it because the data is so hard to share from one team to another. And this lack of data standardization is not just hurting you internally, but it's also hurting you externally as well. Whereas if a great new model drops, and I'm sure we're all very familiar today that a lot of the workflows today are data centric. You're not spending your time building your own models, you're pulling open source models and building on top of them. That if this great new model comes out in the industry and you want to grab it and try it and put it into your workflow, whether that's a new VLM or a new auto labeling model, or it's a great new world model that dropped, you can't use it because your data pipeline only works for your model. So trying to get into a new type of model just to try it out takes months to do and puts your whole team behind, and that cost continuously piles up and up and up. And this is where people like Waymo and people like Tesla, they don't have these problems, right? They have really efficient data pipelines because they're using tools like FiftyOne to really ramp up that kind of production to get there faster, right? They don't spend their time redoing their data pipeline every single time. They're doing it one time. That way they can quickly flex to each one. And this is where the physical AI workbench is really beginning to shine and help teams out here. We're taking you out of the notebook and putting you into a single environment that is completely agnostic to whatever data format or inputs that you're using and allows you to collaborate with your entire team. So no more of these kind of janky notebook scripts that your coworker passed you that's called, test.ipynb and you have no idea how old it is or anything like that. You can always get the latest and greatest information from all of your AV datasets in one single URL. From there, you can leverage a lot of the tools that Katie talked about in the last talk, specifically and probably most importantly, NVIDIA Omniverse NuRec, which allows you to generate these neural reconstructions with confidence that going to get the best quality data as possible. That's because when you load your physical AI data into the Physical AI Workbench, we are actually automatically performing an audit over all those different inputs and data points that you've given us. Over 100 different automated checks are ran from across metadata, timestamp, calibration for extrinsics, intrinsics, making things like active actors, trajectories, sensor projections, and more to ensure that all your data is as calibrated as it possibly can be, right? And flagging scenes that maybe are not the best for your next reconstruction or physical AI workflow. And this is how we were actually able to go into that tier one OEM that I was mentioning earlier, find out that all of their data from 2022 and on was completely miscalibrated. I mean, this is a $50 million mistake that was made because they weren't auditing their data set and being able to understand where these issues are finding in their data set. Just one small mistake, like an incorrect pose transformation or something like that, can drag your model's performance way down. And so with the Physical AI Workbench, we're aiming to make this not only agnostic, so you can transform your data to any dataset format that you need to go to, whether that's some of the open source standards like Waymo or NewScenes or Pandaset, or any of your own custom stuff by a nice, cleanly exposed set of APIs that lets you transform samples and let you get access to all these latest and greatest models without having to rebuild that data pipeline each and every time. This helps you get your data production ready, so you're not having those expensive 8x H100 training runs that fail. It lets you go to your boss and say, hey, I really want to go try out this new workflow. Can I give me a week to try it out? And you're going to have to and be able to do that within that first week. It's not going to take months anymore. You're not going to have those model input mismatches where, oh, I'm missing this one value or, oh, I'm missing that one value. You're going to be able to get the best out of your data set, no matter what is present or what is there, right? A lot of times we only have so many things that we can fit in. I don't have segmentations or I don't know what an azimuth angle is, right? It's very normal and common, even across expert, to have these problems. But with the Physical AI Workbench, we're always going to make sure that we're representing your data set in the best possible light possible. So even if this model potentially has optional inputs that you can add onto it to get better results, we're going to be making sure that we add those optional results each time to the greatest point that your data set can go. Also, this means no more mismatch comparisons, right? This is not the, I give you a model and I promise you it's the best, right? FiftyOne is completely agnostic, allowing you to compare and contrast multiple different models, world models, reconstruction models, segmentation models, LiDAR auto labeling models that you might be deploying and really testing inside of your workflow today. It's all going to be apples to apples, all in one agnostic place where you're not going to have to do these kind of Frankenstein eval scripts that come from GitHub repos that haven't been touched in a year. Everything can be done within FiftyOne. That way you're always using the best model for your project. Lastly, this democratizes your data. As I mentioned, this is more than just an audit. This creates a rich data pipeline for your whole organization. Everyone on your team has access to this audit data set. They can pull from other teams' audited data sets. That way you can get the best data from all the different sources, whether that's pulling from your data lake or pulling from a recent project from a different team. Everyone has access to share and visit and evaluate and understand what is working for every team across your org. So you can finally talk and understand with all the different problems that your team is dealing with. This allows you also to instantly transfer from any other coordinate convention, as I mentioned. If you're familiar with 3D workflows, sometimes you're in coordinate systems like FLU. We'll talk about that in a second, or maybe you're in RFU or other ones. Like I said, we're completely agnostic to the dataset format. Any AV format can be loaded in and then transferred to other ones using our set of APIs. The last feature is the enrich feature here that I want to touch on before we get into some awesome demos here, where a lot of the times If you're familiar with classical computer vision or photogrammetry or AV workflows, if you give me 9 out of 10 of the inputs, I can give you number 10. I can't promise it'll be number 99.99% accurate, but I can give you with high confidence that 10th variable inferred by the other 9. And so now it just becomes a problem of maybe it's not 9 out of 10, maybe it's 47 out of 50. Can I fill in those last three? And so the Physical AI Workbench isn't just inputting and auditing your data set. It's actually taking that data set and based off the audited results, making it even better for all these models to use. This allows you to go from reconstructions that look like this with ghosting and the cars going all over the place to super crisp and clean reconstructions that look nearly one-to-one to real-life information with pedestrians being tracked nicely across multiple different views with minimal amount of artifacts using the NVIDIA NuRec model in this case. What do you do with these reconstructions? Well, this helps you allow you in QA, evaluate sensor plates, simulate your data, and evaluate these world models or agents that are driving your car in a whole new manner, right? One of the most common problems that a lot of these AV developers have is, what if I needed to move my camera? Look, what if my model was better if I just added one more camera? Would it be that much better if I had a camera that pointed straight back? We only have ones on the side and the front, right? This allows you to go into the reconstruction and not have to put new cameras on a car, drive that car for another million hours, and then be able to train on it. We can take real world existing drives that have come from any past year, reconstruct them into 3D, and then imagine that we had that camera. We don't have to go drive. We can do this in a matter of weeks where we can build that whole millions of hour drive with a whole new sensor suite and then train on that to see maybe it will give us the best performance, right? Because at the end of the day, the most crucial resource for an AV or a physical AI developer is time. It's the time it takes to generate data, the time it takes to annotate data, and the time it takes to collect data, right? So if we can lower the amount of time through simulation, then we're going to ultimately get to much better models faster. You can also leverage this by changing and perturbing your scenes. You finally found that scene that was super interesting you, that scene that your model is struggling with. Maybe it's jaywalkers, maybe it's left cut-ins, maybe it's something else. Now you can take that same scene and change it 20 different times using Cosmos Transfer. So in this case, you can see I'm taking a nice sunny drive in California, and I can change it into something even more exciting, right? In my first case here, I can change it to make it a rainy day, for instance, if I'm trying to make something a little bit realistic. Or if you want to have fun, you can make it a sandstorm earthquake as well, right? It's really up to your imagination how you want to add it in, and it's very, very flexible on how you can build out these data sets. So let me jump out here. I'll show you some examples of how this works in practice. Let's hop into our Waymo example here. You can see, if you're not familiar, this is the FiftyOne app that we're looking at here. On our left, we have multiple different fields we can look through. From our audit field, these are all the different audits that our Physical AI Workbench has done on top of our data set to help understand exactly what is happening for the calibration, the metadata for the camera, the metadata for the LiDAR, timestamp metadata, and much more, as well as some audited projections as well. You can also keep all of your normal FiftyOne labels on the left here. When you click in, you're going to see exactly the same frame as your car sees it, from multiple different LiDARs, from also the different angles of the camera, all in one place. We can even see the direction that all of our different sensors are pointing in from this car at the time of capture. This helps us evaluate our data set in many different ways to help understand exactly what is going on as we get ready for these physical AI workflows. But as I mentioned, this is all about helping us understand what is a good scene and what is a bad scene. So we can work up through incremental audits by checking all these different ones that have passed, as well as able to see the different overlays of our sensor. This allows us to overlay things like our LiDAR sensors, for instance, where I can color it by depth and check different alignments. So if I go over to my sample here, each one of these points represents one of the points coming off my LiDAR sensor, and I can check to see overlays of things like how well am I hitting this tree, where we can see the depth changes based on which tree point it's hitting, as well as the trash can and other things as well. This check can be done automatically as well using depth sensors and using depth models to correlate the one-to-one, as well as you can do this over many different scenes. Uh, as I mentioned too, we're data agnostic. So we can do the same workflow on things like the PandaSet dataset. I can do this on the new scenes dataset where we have even segmented LiDAR points that I can color by. So we can see this crisp tree, the road barriers, the car, the road, the building, all have different colors based on the segmentation of the LiDAR, as well as the Waymo example that we were looking at here. Once you've passed your audit, as all of these ones do, as they're high quality data sets, you can then push it into that NVIDIA NuRec model that gives you that high quality reconstruction for you to help build out your simulation and QA workflows. Here we have a comparison. At the top here, we have the real world data, and on the bottom, we have the neural reconstruction data. You can see it is close to being one-to-one here with very minimal artifacts, where once we go into this bottom model, we can now do all that sensor QA, as I mentioned before. Now, I want to point out this isn't perfect. There are still some things that we're learning here, and I would be lying to you if it was saying that it works every single time. So let's take an example where the model struggles a little bit and where we're kind of growing as we move forward here. So I'm going to dive into one example here. We've actually been looking at it for a while here. Let's look at a case where you might have passed the audit from a calibration standpoint, but you're not actually the best data set ever to reconstruct with. So we're going to look at another Waymo example here. Let me lower some of these LiDAR point clouds so we can just take a look at the sample to start with. We're going to look at one sample here. You'll notice this is a very interesting sample for us for several reasons. One, it's raining. We see some rain on the screen here. That's pretty okay. That's going to probably generate a little bit of artifacts for us, but I wouldn't flag just rain as an issue for us. The other thing I want to highlight here, if we go down, we can find that our velocity on our sample here is actually going down. We are going downhill, and we can see this here by our negative velocity in the z-axis. And that is actually the thing that I want to point out here. Where one of the gaps of reconstruction today, especially as it is LiDAR based, is how much coverage you're getting in that LiDAR sensor. So I'll make this a little bit bigger so everyone can understand the example that we're looking at here. And let's look at that heat map again. So here is the LiDAR sample for our first sample here. Let me click in so we get a better view. There's two things I want to flag and why this sample is poorly reconstructed whenever we do it downstream. One, you'll notice we're missing some LiDAR points on the road as we go further down. This is because we have puddling happening down the road here. And when we have puddles on the road and a LiDAR hits it, this doesn't bounce off the reflection correctly back to the car, and it gets scattered and lost, leading to some road blindness down the way. That's not the only reason why this reconstruct's bad. The other one I mentioned was, hey, we're pointing downhill. So take an example of this one, for instance, which is more typical LiDAR coverage. You can see how we're covering over the entire scene here on the side camera. You can see our LiDAR point goes all the way up to the top half of the image. We go back to that front camera. Since we're pointing down, our LiDAR points down as well, which means we're not getting the same coverage as our camera, which is still kind of pointing a little bit more up compared to our LiDAR sensor. This means that our car is functionally blind all the way up here. All there where this LiDAR is not being captured, our car gets very confused because it's overly reliant, overfitting on this LiDAR model in this case. So when we go to reconstruct, all of this will be completely blind and be Gaussian noise. Just something to flag. It'll get better as we get a little bit less LiDAR dependent in the future, but this is a great example of how you can use the Physical AI Workbench and curate using Voxel51's awesome curation tools to say, hey, if a LiDAR point that I projected is not above 50% of my image, if it's not falling in this top half of my image, then this sample is corrupted, right? It means that I'm pointing down. I can do the curation based on velocity, all these different use cases to kind of throw these samples out as it's not really helping my simulations. I have so much data typically as an AV. I have millions of hours. Let's focus first on the ones that are really, really good. And I can kind of come over here, tag this as a poor sample that I can come back to in the future and maybe when my model gets a little bit better. Another example that I need to be honest about today is an example like this. What we see here is a criminal. He's jaywalking. Jaywalking is not good for self-driving cars, as we usually expect people to cross at a pedestrian crosswalk. But of course, we have to be ready for these cases nonetheless. The difference between this scene and some of my previous scenes is that I don't have a bounding box on this guy. There's no cuboids. And so even though I see the shadow of this person pretty effectively, right? If I put myself in my car show, I can clearly see that this guy is walking over here. I can get him on my LiDAR. If I overlay my heat map, sure enough, my heat map looks at the guy. I clearly see a person here. But when I actually go and I reconstruct this sample, this is what we're going to look like. He's gone. He's missing. And hopefully you're not afraid of ghosts as well, because when you don't have cuboids today in a lot of reconstruction workflows, you lose what we call dynamic actors. You notice we didn't lose any of the parked cars on the side here, but we're moving anything that's moving in the scene. We really, really rely on really good annotation to map dynamic actors today to understand the scene. So while you can still reconstruct static scenes very well, so maybe you have a tricky traffic pattern like a traffic circle or a parking lot or something like that. If you want to be simulating based on dynamic actors like people walking across or cars taking dangerous actions, we're going to have to rely on powerful 3D LiDAR ground truth cuboids today in order to get those contexts. Fortunately, the auto labeling field is growing very, very, very fast. These are things that I know that both many different fields, many different companies, including NVIDIA, are bridging into to solve this problem in the future. But as of today, December 11th, this is still a significant pain point that we have. However, if you're interested in learning more about the Physical AI Workbench and how you can get started today, head over to our Physical AI website. I'm sure that Jimmy, and yep, I checked the chat, has dropped this already, where you can learn all about the different features in the Physical AI Workbench, get some comparisons between a poor neural reconstruction without Physical AI Workbench and a good one with it, as well as many more features that are available from using the Cosmos models and others. If you want to learn more, feel free to hit me with a DM or book a demo here. We can also chat offline if you have any additional questions. But for the time being, I'm happy to pause here and answer any questions people might have about physical AI, the Physical AI Workbench, or anything else that I might have talked about in my talk here.